So the next presentation will be presented by Paul Cavillon, engineer in geology and geophysics for FOREXI. And the subject will be optimizing the cost of an horizontal directional drilling project in the context of a landfall.
All right, I didn't forget to unmute myself this time. So good afternoon, everyone. I hope you're all enjoying this web event as much as I am. Loads of very interesting talks by all of my fellow speakers. I hope I can also give you a bit of, nuggets of knowledge here and there to help optimize this SWAC project of ours. Okay, so a little bit of a background check to start. My name is Paul Cavillon. I work in FOREXI, which is a French engineering company, and we're specialized in anything related to trenchless technologies. So from HDD, so horizontal directional drilling, microtunnels, tunnels, auger drilling, essentially anything that requires knowledge in geology and setting up pipes on the ground. I want to talk to you about a part of the SWAC project that has not really been explored yet. We have kind of had hints about it, about pipe diameters and setting up pipes. So it's actually quite important, but I want to tell you about how we can set up the water intake pipe and the water outtake pipes. We usually do it by doing a landfall, which is, setting up a pipe on the ground between the shore and the sea. And we usually use the HDD technique, so the horizontal directional drilling. And, there's been a lot of landfall projects in France, and there have been a lot of interrogation when it comes to those kinds of projects, hence the subject of this presentation. So I want to talk with you about optimizing the cost of an HDD. And of course, it doesn't work. There we go. So to do this, we're going to go back to what an HDD actually is, because I assume a lot of you maybe aren't familiar with the technique. And we're going to go to the different key steps of the project and try to talk about two axes of optimization. The first axis is going to be linked to preliminary studies and essentially boils down to everything we can do before the project is even set up. And the second axis will be drilling operations and optimizing, what we can do after the project starts. And then we'll go into some questions, if you have any. Okay, so what is an HDD, or a horizontal directional drilling? I've put up these two graphs to give you a bit of an idea. So the one on the left is for a river crossing, and the one on the right is perhaps the one that is more interesting for us. It's about the landfall. So HDD is a trenchless drilling technique that will allow us to set up a pipe underground over large distances and under many obstacles with minimal disturbances on the environment. The way it works is actually quite simple. So you set up one of these machines on the left at the entry point and you equip it with a drill bit. So I've put some examples of drill bit on the right. You can see there's different kinds of drill bit depending, of course, on the geology. And we then start the drilling process by pushing steel rods from the machine and into the ground while the drill bit rotates and excavates most of the material. Once we have pushed the entire length of the drilling rod, we unscrew it. The machine reels all the way back, we plug another rod, and we start pushing again. And we do this all the way to the exit point. This is another example of a HDD machine seen from the front. You can actually see the rods being pushed in real time. I wanted to put a video, but sadly it didn't really work. So you have to just imagine the machine pushing. And you can also see some spare rods on the side. Once again, we push these rods all the way to punch out and all the way to the exit points. And congratulations, we have finished the first steps of our project. We have finished the pilot hole. But we're not quite done yet, because the hole we have just drilled is actually not the right size yet. And we need to, make it bigger. But we also want to minimize the pushing and pulling forces that the machine is going to have to produce. So we're going to start the reaming process. So I've put the graph again so you can kind of follow all the steps. It's kind of easy, there's 3 of them. On the right, we have the example of a reamer, which is essentially just a bigger drill bit that we can plug to steel rods. So what we're going to do is we're going to go to our exit point, unscrew the original drill bit, we're going to plug in the reamer, and then we're going to start pulling it rod after rod towards the machine and up to the entry point. We're going to enlarge the hole multiple times, step by step, so we can minimize the pulling forces, as you see again on the graph, until we reach the size that we want. And as a side note, the size we usually try to go for is 1.5 times the diameter of your outer pipe. So this is going to be an important factor for us. Why this specific ratio? Well, because it allows us to minimize the friction for the next step of the HDD, which is also going to be the final step that we're going to cover now, which is pullback. So now we have a hole that is the exact right size for our pipe, so 1.5 times the diameter, and it's time to pull it back. I kind of assumed that while we were drilling and while we were doing all the reaming, the pipe was being welded together and set up so that it can be set into place easily. All we have to do now, quote unquote, because this is actually kind of an intensive part, we have to take the pipe to sea, plug it to the rods at the exit points, and then pull it back all the way to the machine. Why are we pulling it from sea to shore? Obviously, because it's easier to drag the pipe to sea than the machine, and it's a lot easier to have the machine set up on land. So now, there we go. We have our HDD project complete. This is kind of what horizontal directional drilling implies as far as operations are concerned. And now I kind of want to go back to the beginning of the project and try to set it up with kind of the point of view of the engineer and try to identify the steps where we're going to be able to optimize some costs. So obviously, I'm going to be drilling underground, so the geology of the area is going to have a massive impact on the dimension and even the feasibility of the project. So here's optimization number one. I'm not going to jump straight into geotechnical surveys or geophysics. I'm going to call my resident geologist, and I'm going to ask him to tour the area and to study the geological history of the area. And I don't mean just around the entry and exit points, because those are not even defined yet before my project. I need to get a general understanding of the area. Are there any faults that I should look for? Are there any intrusive bedrock formation that are going to be problematic? Are there any important soil discordances that I should know about? But we're not going to stop there. And this is going to be optimization number two. We're also going to ask him to study the geomorphology of the area. Essentially, I want him to survey the marine environment. Sorry, I'm French, this is hard to say. And I want him to tell me about the expected bathymetry of the foreshore area, which is something Alexandra mentioned. I want to know the highest and the lowest points of the tides. And hey, since he's already on site, I'm going to go straight for optimization number three. I'm not going to stop there either. I'm actually also going to ask him to study the general climate of the area. I'm going to ask him about wind strength. What's the general direction of the wind? What's the average wave height? What's the expected length of the surf zone, which is where the waves are generated? Essentially, I want to know how far from the shore I will have to be to work with a calmer sea and allow to pull back my pipe easily. So now I have a lot of information and my project isn't even set up yet, and I don't even know what I want to do. So I might think, well, you know, why do I need all these studies and all this information on an area that might not even be picked as a part of my project? But trust me, this is absolutely necessary, and I'll come back to this. Okay, so now, next step of the project, I want to move on to geotechnical survey. I want core samples, I want pressure meter tests, I want CPT, depending on where you are in Europe, the tests are different. I want lab tests, and I want to figure out what the soil actually looks like. But, you know, we have a bit of a problem. We want to survey an area that is hundreds, if not thousands of square meters large. And the average diameter of a core sample is between 63 and 116 millimeters. And they cost a lot of money, especially if they're done at sea. So how do I make sure that I get the maximal amount of information with the minimal amount of samples needed? So this is optimization number 4. And sorry, I stopped one. I'm going to use geophysics. So geophysics is a non-destructive array of tools that we can use to get somewhat of a, it's quite imprecise, but we can get a foggy interpretation of what the underground is going to look like. And I'm going to use this. So this is an example of a seismic survey, which is usually what we do at sea, because electromagnetism doesn't really work in salty water. And you can see that we get kind of this information of where the bedrock is supposed to be and where we're supposed to be a fine layer of sand. And we can actually use this to determine which position for the core samples would be most efficient. But we're not going to stop there. We're going to do the geophysical survey. We're going to use it to set up core samples and do a geotechnical survey and get actual data. And then we're going to go back to the geophysics and we're going to interpret it again from scratch to make sure it matches what we actually found in the core samples. Using this methodology, we can actually get a somewhat, again, geophysics tend to be quite foggy and very open to interpretation, but we can get a pretty good understanding of the 3D geological map of the underground, or at least an understanding of it. So now I have the data I need. So it's time to start thinking about the technique. This is optimization number 5. Now that I have all this information, and only now, I can start thinking about where my entry and my exit points are going to be. What pipe I want to set up, what technique I want to use, what technique I can use, actually, is probably a better sentence. It's not about saying, well, you know, I want to do an HDD from point A to point B, let me do some studies. This is not the right mindset. I think the right mindset would be, I need to understand what the area is like, and then I'll start thinking about what I can do as far as technique is concerned. So with all this data, I can produce one of these graphs, this graphs on your left, which shows what options we have as far as the length of the drilling is concerned, and all the possibilities that we can work with. This is the zone in red that you can see. Obviously, the longer your HDD is, the more expensive it's going to be, but this is far from being the only factor. There's actually a lot of risks involved with going shorter, and it's the fine balance that you need to find between the amount of risks that you're willing to take and the amount of money it's going to cost you. Length isn't the only thing that we can optimize. We can actually change the technique a lot. So I just gave an example in this graph that you can see on your right. Sorry. This is what we call a blind HDD. So it's a specific technique that we can use for landfalls. Essentially, we're going to adapt a horizontal directional drilling like we saw before, but we're going to stop drilling right before the exit point, and we're going to do the pilot hole and all of the reaming without an exit point. This way, we can minimize the amount of work that we need to put working at sea, and we can minimize the cost of the operations. But again, this is not a miracle solution and comes with quite a lot of risks, as I've just put on the slide. There's a lot more mud pressure, so we have higher frac out risks, which is a big problem when it comes to HDD. And the borehole that you're going to drill is going to be less clean, so you're going to have higher pushing forces, higher pulling forces, and you might damage your pipe, you might damage your machine, you might damage the steel rods, you might damage the tool. It's not a perfect solution. Again, it's a very fine balance that you need to find between optimizing the technique and optimizing the cost. Which one do you want? This is optimization number 6. Okay, so this is what I want you to think about when you're doing a landfall with an HDD. And this is perhaps the biggest optimization of them all as far as cost is concerned. It's going to be a shocker, I know, but working at sea is really hard. And between 30% to 50% of the overall costs of your projects are going to be related to working at sea. As you can read on the slide, sea platforms, which are absolutely mandatory, whatever technique you use, they cost a huge amount of money, and well, bad weather conditions can just completely cripple them in their efficiency. And it can even completely stop the job site, which is the absolute worst scenario, because you have all of the material on site costing you money, and we are not drilling anything, which is absolutely terrible. So if we think about it, we kind of go back to optimization number 5, which I was talking about before, which is the order of priority. As I've told you before, you just cannot pick the entry point and the exit point of your project. I won't say at random, but without careful and informed consideration. I understand that there's a lot of constraints that come with picking the exit point of your pipe, and you know, a lot of my fellow speakers have talked about different constraints that they have. So we need to stay away from fishing areas, we need to stay away from environmentally friendly areas. We need to make sure that there aren't any abandoned explosives or shell nearby, which is actually a very relevant problem in France, especially in Normandy, if we're going to work around the channel, as Alexandra talked about. If it's a water intake pipe, the quality of the water and its properties are going to be extremely important, as Theo explained during his talk about aquaculture. If it's a water outtake, then the dispersal rate and the shape of the plume that we're going to be, well, releasing in the ocean is also going to be very important. As I mentioned before, we also need to stay away from the surf zone, so where the waves are generated, to minimize the amount of work that's going to be related to working at sea. And we need to essentially make sure that the currents, the wind speed, the wind direction, the average wave height, and all of these parameters can kind of work together and allow us to work at sea. That's a lot to take into consideration. Those are a lot of parameters. And this is exactly why I want to circle back to the slide I actually skipped before, so to this slide, which is preliminary studies. I want to leave you with this. There's one thing you must retain from this talk, is that when it comes to setting up intake pipes or outtake pipes, preparation is the key. we have a bit of a motto at my company. We always tell our clients, and so far we haven't been proven wrong. I would touch wood, but I don't really have wood around. We always tell our client that an HDD project that is well prepared is a successful HDD project. Think of it like a grandmaster chess player that's just going into a tournament match. Or, you know, if you're following a bit of the events lately, a football team that's about to head into quarterfinals of the World Cup. I don't know if you're following it. But preparation and a good understanding of the obstacles that are going to come around when your project is actually started is by far the most important part of any project. And some preliminary studies, especially when it comes to directional drilling and when it comes to geology, a lot of the things we hear from our client is, well, some preliminary studies are kind of useless and kind of costly. And, well, we don't want to do studies in a zone that we're actually going to later not use. This is just wasting money. And I really want to insist on the fact that you cannot optimize a project that was poorly designed from the start. Like, if you pick the wrong zone and if you pick the wrong exit points, I'm not going to be able to optimize your project for you. And it's going to cost you a lot of money, and it's going to be extremely complex to figure out a way to optimize anything. So yeah, that's it for me. Thank you for your attention. And well, if you have any question, now would be the time. Let me get back on the conversation. There we go.
Thank you very much, Paul. That was really interesting. Okay, yeah, indeed. If some people have some question,
Okay.
That's the time. I don't see. Okay, we have one from Martin Brown. So, assuming you have done this optimization process, typically, what is the largest cold water intake pipe diameter that you can back ream?
So with an HDD, with the HDD technique, which is actually one of the techniques we can use, but we can also use a few other ones. HDD is quite limited when it comes to pipe diameter because we very quickly have extremely high pulling forces when it comes to pulling the pipe. So I would say like around, I don't want to give you any information that could be debunked, but I would say around 1.5 meter would be the maximum for HDD. But the good thing is that we actually have other techniques like direct pipe, or we can even go for a microtunneling technique. And there we can go like to 3 meters, 4 meters diameter. So we can actually go pretty large.
Okay, thank you. Is there other questions?
In general, is HDD less complex for shallow water SWAC than deep water SWAC? It actually only depends on the geology and the nature of the pipe that you want to set up, because the geometry of our drill is going to depend on, well, obviously the bathymetry, but it's mostly going to depend on what soil we're going to be confronted with and the geometry of your pipe that you want to set up, because we're going to have certain curve rates that are acceptable. So I would say HDD is equally complex for shallow water and deep water SWAC, but it can be used for both, I think. It's not really comparable. I think the complexity is pretty much the same. Yeah, oh dear, that's the right answer.
Okay, thank you. Okay, I think we don't have any more questions for now.
What about self-burying pipes? So there's actually a technology that I was about to talk about in the roundtable, perhaps if I had the opportunity to. It's called direct pipe. So that's kind of a self-burying pipe, but for a much bigger pipe. Because the problem with self-burying pipe is that you have a very limited diameter. You tend to go very small in terms of diameter. Direct pipe is actually a technique that mixes self-burying pipe with microtunneling technique and kind of HDD. It's kind of a mix. And as the name suggests, you directly set up the pipe. So it's actually very, very innovative, and it's being used in a lot of landfall projects all across France right now. So that's actually a very good solution that could help us optimize the cost of such projects. But we have very limited returns so far on the use of the technology. And it has its own constraints as well. It's not a perfect solution. Do you do all seismic surveys by yourself? So as far as FOREXI is concerned, we don't actually have geophysics material. We're just an engineering company, but we know a lot of geophysical companies around France that we work with quite often, and they do seismic surveys at sea and onshore. They also do electromagnetic surveys at sea, because I think like one of the technologies actually allows us to work with electromagnetism in seawater now, which I was always told didn't work, but apparently it does now. So.
Okay, thank you. Um, I think that's it for now. If there is more questions, like they might be asked during the roundtable.